We are here to celebrate Fernando Montealegre-Z's inaugural lecture, where he's going to tell us about the impact he's made and his journey through his scientific life, I hope. I am going to stop here and let Professor Libby John, the Pro-Vice Chancellor of the College of Science, introduce Fernando more appropriately, and then she will hand over to Fernando to take care of the rest of it. Thank you very much for coming.
Thank you to Stuart. So, Fernando Montealegre-Z was born in Colombia, in a little town called Palmira in the west near Cali. In his childhood years, he showed a strong interest in science, mostly trying to explain how things work. He spent hours a day playing with insects and observing their behaviour and anatomy, the benefits of which I think we're going to hear a lot about today. So it was no surprise when he decided to study entomology at the Universidad del Valle, Colombia. He graduated with honours for his dissertation on the taxonomy and systematics of the Catidid family, found in the province where his town is located. This was pioneering work, the first attempt to organise the systematics of this family in Colombia. Along the way, Fernando found many unknown species, which he later described. His minor field was biophysics, and he became interested in bioacoustics at this time, which again we're going to hear a lot about. In 1999, he joined an MSc course at the University of Toronto in the lab of Professor Glenn Morris, followed by a PhD programme with a thesis entitled Biomechanics of Musical Stridulation in the Tetigonidae, which I'm sure will have explained to us today. He's oversaw the integration of innovative techniques such as high-speed video, motion detectors, and laser Doppler vibrometry, which contribute extensively to the field of bioacoustics. Through international collaborations, he received training in electronics at Erlangen and Kaiserslautern in Germany, and learned the design of circuits for lab instrumentation used in animal and human physiology and biomechanics research. He then joined the lab of neurobiology and acoustics led by Professor Andrew Mason as a postdoctoral fellow, also at the University of Toronto, and then secured funds from National Geographic to investigate the ecoacoustics of extreme ultrasonic tropical insects, which sounds fascinating. In 2008, he was awarded a postdoctoral fellowship from the Human Frontiers Science Programme to study the biophysics of insect ears. Luckily for us, Fernando took this grant to England to the lab of Professor Daniel Robert at the University of Bristol. The discovery of the cochlear organ in the ear of catidids and the demonstration that the ears of these insects were more sophisticated than previously thought, having outer, middle and inner ear components, just like ours, was a major contribution of this collaboration. Even more luckily for us, in 2012, Fernando joined the University of Lincoln as a senior lecturer, overseeing the development of the invertebrate zoology and forensic entomology courses, and taking part in the development of our zoology programme. He has been funded here with grants from the Royal Society, Leverhulme, NERC, and the European Research Council. And as with these funds and the university's investment, he's been able to build up a fabulous lab with state-of-the-art technology necessary for interdisciplinary research, making Lincoln one of the 4 unique places in the UK with technology for microscale hearing research. In December 2017, he was promoted to professor, so our series has got a little bit behind, I think, here. But that's wonderful, because we're all here today. His current admin duties include coordination of our UO86, which is one of our REF submissions, and he represents the university in an agreement between Lincoln and the Uruguayan government for doctoral studentships. He leads the labs of bioacoustics and sensory biology and imaging. He's supervised 8 postdoctoral researchers and 11 postgraduate students, and some of them, I think, I can see, are here today. Fernando is now considered one of the world leaders in insect acoustics and micromechanics. And his expertise in acoustics and vibrations has allowed him to contribute to other fields like animal-plant interactions, such as bee pollination, and amphibian and reptile bioacoustics and mammalian hearing. He's contributed a book chapter for high school and college students. So that's Fernando's academic history. But of course, there's much more to Fernando than that. And I'm delighted that his family are here with him today. And along the way of that academic story, Fernando has had many incredible adventures, which I'm sure we're going to hear more about in due course. I've had the privilege to travel on field trips with Fernando. He's a fabulous person to go on a field course with. He plays the guitar, which is an essential attribute for a good field course companion. He always starts the dancing first at the fiesta, and he tells the best stories. So I hope we're going to hear some of those stories along with his scientific journey here today. So over to you, Fernando.
Thank you. Thank you, Libby, for this wonderful introduction. I think you saved me a lot of time. I'm going. This half of my talk is already there. What she said. No, I'm teasing you. Thank you, Libby, for the wonderful introduction, and thank you, everyone. I'm really happy to be here. I've been looking for this lecture for 2 years, honestly. Yeah, I think I feel more comfortable to be interacting face to face with people for these kind of lectures. So I'll be talking today. So my name is Fernando Montealegre, for those of you who don't know me. And I like studying, investigating, or learning about animal communication. And I also like, of course, to transmit, teach other people this information. And this, I studied how insects, specifically how insects communicate. Why is this important? The important part of insect, we have sound everywhere. This is part of our daily life. Just think about what the first thing you heard this morning. Lots of you will perhaps converge. The first thing I heard was the alarm, in my case, and then some people around and toilet flushing and all of these, the regular things in the house. And then the acoustic space was dominated by my wife after that. That's them. But in general, this is, of course, sound is very important. Acoustic communication, human speech, animals communicate, and there are animals that communicate with sound that we don't imagine they exist. It's just so high that we won't be able to hear it, as you know. Okay, so this is I have divided my talk in these main 4 topics. We'll just talk about a little bit of my background, how I became a scientist, and I will present some important steps during my career, and then I will talk about the science. I was born in Colombia, in southern north of the little province called Valle del Cauca. That's what Libby described. And this is very, the location is very particular because it's just where the Andes divided in these 3 regions. and the town where I grew up is in this valley, and most of the cities are located there. The main product in this area, agricultural product, is sugarcane. But we have the benefits of having in here we have the lowland rainforest of the Pacific. Then you get these hills, and the slopes of these you'll create a different thermic floors that create a lot of diversity in flora, fauna, and different types of forest. So all of these animals will eventually converge, at least in the 70s when I lived there, in the cities. They will come. This is just basically just a cross section of the valley. So that's the city from a view, very small, surrounded by sugarcane. I grew up in the house of my grandparents, my mom and my brothers and sister, and these are my grand uncles, my grand aunt. And I just remember the first thing I remember, this house still belonged to the family, and that pot that is there, that's my memories, the early memories I have of my life, playing with ants. And it was this species, this Ectatoma rhythm, and I observed this ant probably since the age of 4 up to when I was probably 9, just every day playing and collecting them and getting a lot of stones because this group stink. And one day, at the age of 9, I decided I wanted to see how the nest, work inside, and I just put them in a bottle, Coca-Cola bottle, by the way, and put some sand and the ants, and began to learn. But I realized that they will not prosper if they didn't have the mother, the big one, which is the queen. Of course, I began to understand this without any knowledge of reading books at the time. Just it was something, and I keep this observing in this kind of terrarium, these ants, until I was probably 17 years. They have different nests, different kind of. When I was 17, before I joined the army for 2 years, and no one was able to take care of the ants, so the ants disappeared. But I was observing, I learned a lot of things, of course. I didn't know the scientific names of the I knew the pupa and how they will take care of the young ones, the eggs, how well organized they were with the garbage, all of these things that you see in the books. I saw that there. So it was in the backyard of the house is huge and still has a lot of fruit trees, and from the topography I described, all of these insects will fly during the daytime and at night. And at night these were very common visitors. It's very common species of katydid. This is the name I'll be using here, katydids, and in Europe they are known as bush crickets. So this same species, and some people believe that those, of course, the natives, you can imagine all the myths, that those are good luck. If you see one of those, it's good luck. But you find these ones, no, it's not a good thing. So that was natives, you think, used to think at the time. There was some other, this more exotic actually, these species, that it was probably 1975 and 76. I'm very good with dates. Just not, and because I used to play with this one with my brother, and we don't see, and this species disappear from the cities. They're more vulnerable. Of course, with the expansion of the sugar cane, and all of these species just were relegated to the mountains. You still can find them, but you have to go to the mountain. They used to go to the cities back in the day. And going back to this is a really nice story because discussing one day, talking with one of my mentors, Daniel Mills, about who inspired you, this. And this, my two uncles, they work in the construction business, and they were making pools for rich people, in the hills of the mountains. And they will build these pools, and they stay there for all the week. And they will come back home during the weekends. But the pool lights, all of these attract a lot of insects. Now they're in the mountain close to the forest, and they collected this insect for me and they brought it home. And that's how I began, because they knew that I had the passion for insects. Something that I really appreciate from my family and the people that was surrounding me is that they never opposed that I was going to study entomology. Because in developing countries, usually the parents, the families force actually the kids to go to medicine, go to engineering, something that generates money right away after graduation. And this is, but I didn't have that, and I appreciate this. And then I began my insect collection. It's a very very primitive start, but I knew that insect could be pinned because some relatives, some people in my family were studying biology, and they have to do these collections. So it was more or less at the time, 12 years old probably, I was playing football. Football is a big sport, as here in England there. Playing football with some friends in the football field close in the neighborhood. Coming home, and I found this one. This is not a katydid, this is a cricket. The normal crickets are ground dwellers. And I found this one running during the daytime, which was very rare because they're nocturnal. And I took this animal, I just got it, put it in a bag, I took it home, and then put it in a little jar and gave it some fruit. I think it was watermelon. And I was seeing the animal, eating, and also this one, seeing the animal, and then when I went to bed, the same, I forgot that I had the animal in my bedroom. I just went to bed, and more or less at 2 in the morning, I was having nightmares. And then something was very annoying, bothering me. And then I just woke up. It's a very noisy thing in my room. And then I turned the light on. It was something like this. I turned the light on, and the animal stopped. But I didn't know it was the animal who was singing, and I just turned the light off again. I went to bed, and the animal. So this, and then I realized that the sound was coming from the jar. I said, "Oh, this is this. What is he doing to make this noise?" And then I turned the light on again, and the animal stopped. And then I just got really close, turned the light off, got close when I saw, because the animal didn't stop immediately, he had some inertia. So I saw him moving the wings. I said, "Oh, that's how you bastard generate the sound." So that's what, okay, so that was my experience. Then it was too loud. I put the animal out of my room, and it was still, I could hear it. And then I took it to the backyard in the little cage. But next day, I went to look for him, and he was being, the fruit attracted ants, and the ants killed him. So that was the end of the animal. But this is a very common group. This is a trilling cricket. And then I have I was lucky, and this is the high school where I attended. It's a public high school, and I was lucky because in year 7, I had one of those inspiring teachers. This is Leonardo Valencia, and hopefully he's connected now because, of course, obviously he's retired now, but so he had founded a museum in the school, and so he got donation for specimens, preserve different animals, plants. So we had a small museum, and he was looking for volunteers to help him just curate the museum, just clean and organize. And I discovered that he had 2 cabinets of insects. They were already pinned, and they were just looking, he was waiting for classification. And he taught me how to pin, how to clean, and how to label them, and how to use these guides of insect identification. My best friend and I used to go there on Saturdays, because we volunteered for this. So I learned basically the order names at the time. And then, for some reason, I have fascination. The same year, I developed a fascination for bullets and projectiles. And I say, because you cannot see them, how fast, I think that roots to the fact that you see in the encyclopedias for kids, in the books we have, you see how these old scientists calculated these velocities, and you see the old lab, and I was completely inspired for that. Other kids were doing something else. I was just completely focused on, I want to do this. I didn't have a gun, of course, And I say, "Yeah, but I'm going to generate my own bullets. Just wait." And you say this is the pen. You know? And then I say, I want to miniaturize everything. I can do the experiments at home. And my idea was that you get one of these brass points, just like that, and they say, if you put it, you dry the ink and you put some powder and get a barrel, something like that, and you can get the ignition. I'm pretty sure that it will shoot, and then you can calculate. And Julia, my best friend, was okay. Let's do it, and we were doing it, and it really worked. But it was very loud, because all the sound will come from the back, and we began to improve the experiment and make it. How do you say in English? Muffler, eh? Something like stop the sound. And because my uncles were very annoyed by this, they still remember that. They were very annoyed by this, and then we spent. This is what actually I visited my mom, and she has some of my notebooks from high school, and that was the original drawing. This is I visited my mom. The last time was 2018, and that was there. So I just took a picture of that, and we spent a lot of time shooting potatoes, because I knew that if you get a big potato and you shoot it, the bullet will stop somewhere. And that will leave a trace, and that trace will give me a hint of how fast. We failed, of course, in the calculations, but I did it when I went to the university in biophysics. I just talked to the professor that was teaching me, Edgar Diaz, I remember, and I did it just after that, because it's something that you have to do it, you know, even when I was already too old. Okay, so then I went to the university. I knew that I was going to study entomology. Most entomologists there, because the region is agricultural, they will go to do agricultural entomology, to work with insect pest control, and that was my plan. Even when I just don't kind of like it, but if I have to do it, I have to survive. I will do it. Then in the university, this is my supervisor. The undergrad programs there at the time were very long, 5-year program, and then you graduate as a proper entomologist, or marine biology, or botany. You know, they have these areas, and it's kind of similar to here. You know, at the beginning you all converge with all your friends, and in the third year they will divide into the different programs. So Ranulfo he's a medical entomologist working on public health entomology. And but he was fascinated by the katydids as well. He said, I love these animals, but we just don't have someone here to study them. Why don't you do it? And I said, okay, I was fascinated. He's offered me a whole thesis on this. So, so I began, but he said, the only problem is that we know nothing about them. So you have to start from zero. And I say, okay, so we can, we had internet, there were no PDFs at the time, so finding articles was really difficult. And we had all I got at the first instance was what we could get through university loans or what was already in the library. And then I began to contact, we had internet in the university in those days, the first organization of the internet, and I began to contact authors. And a lot of people, people want to help. Some of them send me photocopies, of the big packs of papers, and that's how I began. I realized then that most of the literature was in German, just to make it worse. So because English, because we've been taught English in high school, and also we could read, but German. And then I was completely disappointed. And my wife, is an engineer, she's here, she was studying at the university, and I said, it's very easy, just go to you still have 2 elective courses to take, go and take German, the university will give you this for free. And then, okay, I did it, I learned the technical test, the technical aspects of this paper, and I completed a thesis. And then the idea was to go to the different places, natural parks, and collect animals from different areas, specimens. And my wife, of course, she was my girlfriend at the time, she would help me in different aspects of field work and motivation, of course. I completed the thesis and provided keys for the identification, as you can see. They are my own drawings. And produced 4 small papers in Spanish, but they were just providing the keys for the identification. And these were enough for me to secure a scholarship to go to Toronto. In the process, I met Glenn Morris, my PhD supervisor, and he got very interested in he helped me with literature. He sent me boxes of papers at the time. And he was interested because he was working in Ecuador. But of course, Colombia, for this division of the Andes, the biodiversity is amazing. So he wanted to go, and he visited me during my dissertation, the research that I was doing, a couple of times. The first time the university offers a full TV documentary in the university channel. And so we had a lot of time. From this experience, we discovered this animal, which I will talk about. This is the most ultrasonic animal on the planet. Which I let one of my PhD students actually later described. I let him to go first author because he has been studying them later for a long time. And we described a genus with 3 species, all of them super ultrasonic. That's what the name we give to the genus Supersonus. Then in the graduate school, I had to divide my time into field work, chasing birds here, and doing some teaching because it's mandatory to do a lot of teaching in North America. And I did field work in Canada, of course, Central America, in the Pacific lowlands, in different places. Here's one of the last field seasons we had in Gorgona Island in Colombia, and here's Glenn Morris and his wife as well, and Fernando Vargas, who some of you might know him. He's my friend at the university. But I want to point out something here. This is one of the anecdotes that Libby probably was referring to. So this is the first field season we did to collect katydids, and the question of my PhD thesis was the main question: how these insects generate musical signals in the ultrasound. That's the main question. And then, of course, we have to go to and collect as much species. These species are nocturnal, and we were collecting in this area, and I forgot that these guys were there. This is the rebels, and they found us. It was more or less 8 at night, and we were with headlamps, and they just came. They arrived, and it's a lot of boots standing there. Just calm, don't panic. What are you doing here? This is our territory. So, well, I'm looking for insects. And they didn't believe us, and they took us to the campament for 6 hours. It was very scary because I had everything I wanted at the moment. My studentship, everything to go to Canada. This was the field trip to collect the first specimens I was going to use. But luckily, we have collected these 2 specimens. It's a species I described later as Panacanthus intensus, and another one of the ultrasonic ones. These are the most relevant in my thesis, actually. We have the 2 in small containers, and the guy just couldn't believe me that he was catching insects. And I said, well, here they are. So what do you study on this animal? Well, I studied sound, and then it was a long discussion that I can tell you. It's really funny at the end, very impressive as well, what the guy told me. And then he let us go. So we just, that was the, and that picture on the top shows why the male life insurance is more expensive than female. See? That was the challenge with Fernando Vargas, and then we go there. But we had certain peace of mind because the natives say they didn't have accidents there. But it's still no good, huh? My graduate students don't do that. Okay, now let's go to the main finding. This is science already. So I was studying how these animals produce pre-tone signals, musical signals, and a musical signal is just like that. It's a way, and this is a second, and in this case we have 4 cycles, and the frequency will be 4 hertz. It's very easy. When you increase the frequency in the same second, in this case 50 cycles per second, 50 hertz, And this is characterized by this just very sinusoidal and sustained. Looks very simple, but only structures made by devices made by humans or by evolution, by nature, like the vocal cords, the larynx, are able to produce these, such as tones. And they are characterized, of course, if the amplitude is constant and the frequency is constant, the spectrum is going to be really narrow. That's the spectrum of any musical instrument. Very narrow, with some harmonics, but that's the characteristic. All of these animals are endowed to do it, frogs, insects I studied, birds, and some of these mammals, because they can vocalize in the musical signal. That's the difference is broadband signal, which are designed usually in most animals as a deterrent to defend themselves or to warn other animals. Like the hiss of the cat, the rattlesnake, and of course the waveform is more complex, amplitude and frequency variation, and the spectrum is broad. And that they do it because they want to guarantee that any predator hear them. They don't know the hearing range of a particular predator. They have to make a broadband just to make sure that any predator hear them. And this is it. I'm not sure if this might be too late now for me to. So just a little test here. So if I played 1 kilohertz, see this is 5 kilohertz. Anyway, I think it's too late. The system will not let me play from there. No, it's not working. Anyways, so if I play 5 kilohertz, it will be a beat, a tonal signal at 5 kilohertz, and then 10 kilohertz will be higher, and 15, and then you begin to see that, you begin to feel that your ears don't work as above certain frequency. Mine only go to 16 now, because the older you get, of course, you lose more sensitivity. And 20 kilohertz is supposed to be the boundary for ultrasonic signal. Above that, this is the ultrasonic range, and a lot of animals can hear or can communicate this signal at this range. And it's something to bring your attention. When you go to the forest, any forest, you hear the birds, the insects. But interestingly, this was measured in Panama in the rainforest. And this includes the ultrasound. The amplitude of the sound, so the measured in decibel, the background sound, is very low during the daytime. Those things that you hear, but at night it will increase it a lot. And there's a lot of animals singing there that we don't hear. And that brings, of course, this statement of my PhD supervisor. People need to always be aware of frequency response when they record or broadcast. So, because a lot of experimentation, people go without specialized equipment and they're not careful, and the insects don't respect audio. In the insects, what he means, of course, that there's a lot of things going on in the background that we cannot hear. The relationship of these animals I studied, these are the Tetygonidae or the Katydids. Okay, these are the Tetygonidae, and they are related to these Greeks, and they are related, and they did the birds probably in the Permian to the modern crickets. See, that's how this is very brief phylogeny. The Katydids come from an ancestor that went extinct back in the Cretaceous, probably. But all of them have in common that they produce sound for acoustic communication. That one just is extinct, and this one is a very successful group with more or less 8,000 species distributed everywhere except in the Antarctic regions. And these ones are going extinct. It's interesting. They're more or less known from the fossil record, but there are 8 species living in cold places, in temperate places, in Canada, in China, and Russia. I believe these animals are very sensitive to climate change. they will probably disappear. And we're trying to study them actually. And the crickets, they're ground dwellers, very successful group as well, crickets and more crickets. So here, so you can now see the diversity. This is the same it's a summary of the phylogenetic tree, but this group has been very successful, and you can see now, while these ones stay in the ground, they have colonized, the katydids have colonized just many habitats, and they exploit a lot of frequencies. These ones stay more or less between 5 kilohertz and 10 kilohertz. And it's amazing the diversity. And a lot of these adaptations, most of them are nocturnals, and these adaptations are to avoid diurnal predators while they are resting, like birds, the main predators during the daytime. So how they produce the signals? The crickets use the wings, as I mentioned from the beginning, and they all have the katydids will do the same as you'll see in a minute, but they have the ears in the forelegs, and I talk about this. So it's the male calling the female, and because they sing from the ground, it's better for them to do low frequencies. 5 kilohertz is a low frequency, and it's the best frequency, has been shown to propagate close to the ground. But they're too small, and they will be, the wings radiate, they produce sound more or less like this. That's basically what they do. And they're too small for the wavelength they generate. So if they are small, if they're generating sound like that, they don't have something good to radiate the signal. The wings are still small, the wings are the radiators, but it will happen something like this. I'm generating sound there, but the sound is interfering with itself in the machine. If you have a radiating surface, like okay, this is so that's what happened to this animal. They're too small for radiating the signal. So okay, sorry. So they produce the males. They are trying to put the help with the radiating area of the burrow a little bit, and most of the sound now is radiating being radiated to the front. So they do it this way. You see, this is cricket. This is a chirping cricket. The first one I showed you was a trilling cricket. This is a chirping cricket. And what happened here is that the wing, one of the wings, the wing on top, will have this serration of teeth. It's a vein with teeth systematically organized, and every tooth will generate, when it's being scrubbed by the plectrum in the other wing, every tooth will produce one oscillation, and if the oscillation is sustained, they will form a complete pulse. And then I'm going to show you this in the following video. So this is low motion video. Now, hear that the decaying frequency as well. We don't hear it in the initial. We don't resolve that at the normal speed. So the cricket is in the back, and this is the plectrum going down the file, and in this action, the plectrum loses velocity by the default muscular contraction probably, and that would produce this. Is what you hear was these are the syllables. Every syllable doing one closing stroke, and they produce. This is the frequency modulation. Woo, 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 and that is the signature that the cricket is singing. They all modulate in the same way. Interestingly, each male in a population will modulate differently. They have their own fingerprints, but in general, all of them will modulate. And this is the spectrum, just narrow, as musical spectrum. So the two wings have to synchronize and radiate sound, because it's better to use two radiators because the frequency is too low to maximize the area. This is a laser Doppler recording, and this is no modeling. This is the real data of the animal is being stimulated with sound. Some others, to avoid this problem that I'll show you here, too small still to radiate low frequencies, and they use these baffles in the wing to avoid the interference of sound on the back and on the front. So they do. Some others do the sing from burrows and use this as an exponential horn to amplify the signal. Katydids don't worry much about the size of the wing because they use high frequency with short wavelengths. It still might be a problem for them, but look at this one. It's singing. he's singing. But now, the microphone of the camera doesn't record ultrasound. It's just a normal microphone. We put the microphone on the same species and record. This is singing at 30 kilohertz on the microphone. So like slowing down so that we can hear it. It's being slowed down. It's a very pure tone signal. And now I think we are hearing probably, I don't remember how much I slowed down, but it's probably 12 times. So, but it's a very pure tone signal. So they do it, they do this with same as cricket. They have a plectrum and a file with teeth, but notice that the density of the teeth is higher because they need to generate more oscillations per second. So basically, the number of teeth is a way to multiply the low motion of the wing into a lot of oscillation that at the end will reflect in the pulse and reflect the frequency. These are all of them singing at night in the ultrasound. You know, that's how the ultrasound should have been. You know, if we were able to hear it. So the different species. And now I was telling you, this is they radiate sound with only one wing because synchronizing the two wings at that's such a high velocity is very difficult and destroy the sound. It will damage the signal. So they will radiate sound with only one. They have evolved for radiating sound with only the other wing is down, as you see there. One thing that I came from, and this is very common, this correlation, and Carl Saburi and I have been working on this for quite a while, but in my thesis, my PhD thesis, I showed this correlation. Basically, the size of this stereodilatory file, the file with teeth, correlates with the frequency. So large files produce low frequency, and small files, high frequencies. And same with the sound radiator. The radiation area correlates with the frequency as well. So those species, every point, by the way, every point here is a species, different species. So the size of the radiator, large size will correlate with low frequencies and small size with high frequency. This is important because if you put any animal, a dead animal, you have the morphology, you put it in there, you can investigate how this animal was singing, what the frequency the animal was using. And that if you put a fossil, you can predict the frequency based on this correlation, of course, and finding I'm not showing the equations here, of course, but there's no need. So it was in more or less the same parallel to this one. I described the mechanism of this animal making sound, and this is the wings of these animals are too small, and they are so fragile, and the muscle will not be able to move the wings to generate the 150 kilohertz. Can you imagine? This is the human range here, and these animals are just sinking just really far from. And the way they do it is that they move the wings softly, but they deform the plectrum and store elastic energy and release it as a spring, and that's how they achieve the velocity of tooth contact to generate that frequency. And so we published that, and that was actually included, included in the Guinness record. They picked it from the original description. We published this in the Journal of Experimental Biology. It was one of my thesis chapters. And if you go this in music now, if you get 150 kilohertz, that would be more or less the equivalent to the 13th octave of D. It's really high if you put it in there. Why this is important? I don't know if you remember. I'm not going to go into fine detail, but in 2016, the employees of the American Embassy in Cuba complained that sound was disturbing them, and they were being ill, and that was debated. They have all of these symptoms that you see here, and the government blamed a sonic attack. The American government, and they took the employees out. So they reduced the personnel by 60%, and they were beginning to. So this is what before Obama was the one who was trying to negotiate and put the embassy in Cuba, but the government of Donald Trump was, you know, accusing that there was something going on there.
The recording gives us the first tangible sense of what it was like for these American government workers in Havana who were hearing these unexplained sounds in their residences and later developed physical symptoms.
That reminded me of my childhood. Yeah, I was in Paris when the news came. I was doing work in the museum, and one of my colleagues there showed me, "You hear this?" Yeah, that's a cricket. I knew that it was a cricket right away, but I didn't do anything because I didn't want to get into trouble. But then, and there was a lot of debate after. Some people say, "Oh, this is only there's nothing happening. This is a mass hysteria." You see here, there was a lot of things going on if you read the story, anyways. And then until this boy. Is a PhD student of the University of California, Berkeley. Is the son, actually, Alexander Stopp, is the son of a very important scientist in Harvard. He's an astrophysicist. And he contacted me and said, "I think you can," he had done some calculations already, "but I think you can convince people that this is a cricket." And I said, "Okay, you are American. If you don't care, I don't care." So I did the calculations of he had already identified with the potential species, 2 species. One was a katydid and the other one was this one. And so basically we got some of these species from the Orthoptera database, because this is from insects of North America. And because this is the recording, you can see this is trilling cricket, and you can see the syllables here if you amplify. The sound of this animal was like that. Continuous trill. Can you imagine? This is really loud. The decibels, I've measured this, and the intensity is about 120 kilohertz. This is if you get close, it's close to ear pain. So I did the analysis, you did the syllables, and got 2 syllables from there, and frequency analysis, instantaneous frequency, and you can see that woo, the same as all crickets. That's nothing, not mysterious. And then we got the sound that this guy put because it was available in the internet. This is the danger sound of the APA agency. Of course, they say that the sound was recorded inside the room, and that's what it has a lot of echoes. You can see the echoes here reflecting back, but occasionally you get a few syllables, and then I try to isolate 2 syllables with less echo, and did the frequency analysis, and you get the whoop, whoop again. And the variation, the difference is because every individual modulates in a different way. So we tried to publish that, and we couldn't, of course, because there was a hot potato in the mouth of editors. Now one wanted to do, so the paper was in Science, was in Nature, and I understand Science because it's an American journal, but in Nature, Henry Gibb was very skeptical at the end because we have only one recording. There were 8 available, but we could only access 1. Anyways, we decided to put it in, I was very skeptical to put it in bioarchives. It's a free repository, but at the end I agree, because I was skeptical because we haven't published the paper at the time. We haven't published yet, actually. But after that was uploaded in there, so now it was in the news. Because the journalist speaker, it was all the Cuban, the Sony attack cricket, and you can imagine the whole controversy this created. And there was in Twitter, and a lot of things, a lot of controversy, people in favor of the war we have done, and some of the people against, obviously. And Alexander, being American, being threatened by Americans, being called by Americans traitor, some of these extremists. So we were, at the end, my wife told me, "Don't get involved in this, Fernando. This is too far already." And so we stopped it there. We didn't give any interview. We stopped there. We didn't give any interview, but I didn't want to give because my paper was not out. So that's all the reason. And then I got things like that from in Science. So it was all over. So this is some jokes. Actually, some scientists, supporting what we were doing. Until, of course, the new administration ordered a new investigation, and this Jason group is an elite of scientists that do work for the United States government since the Cold War, and they investigated, and they say, "Yeah, that's a cricket." Okay, it's in this report, And then, of course, that so the illness that these people complain, no one knows what the explanation. But the president signed up this act, the Havana. You can read this on the internet, the Havana Act, and then they changed the rules again and had some. And the embassy is back now. You see, that happened this year. And then this book, this guy, if you want to read, this is a good explanation. It's basically, this is just map psychogenetic ignorance. There's a good explanation of what happened. It's really, I enjoy reading this book. And of course, they put in the cover the cricket. Actually, that's not the same species, but. Okay, now let's talk about other stuff. The importance of this research also was related to a long time ago, 2012. I got contacted by some Chinese paleontologists, and they claimed to have found a cricket in fossil with the wings open, very rare specimen. Actually, you see it there. The two wings will have stridulatory files, as you see the veins with the teeth, and he asked me if I could calculate how this animal was singing, and then I can try. He sent me good pictures, and I began the calculation just by putting the animal in the graphic I showed you, and estimated a frequency of 6.4 kilohertz, 6 kilohertz more or less, I would say. And then with an algorithm using the anatomy of the file and this basic frequency, I recreated this pulse, and then. That's the maximum I could do, because the rest is behavior, and behavior doesn't fossilize. So we imagine that the animal was singing more or less like this is a small reconstruction based on living and the fossil wing. The animal was singing this 6 kilohertz, serenading the dinosaurs, and that was more or less. And of course, when we published this in PNAS, it was all over because kids like this story. And the way the journalists transmitted this was very good, actually. I'm not being a paleontologist personally, I really enjoyed doing the work here. So that has some impact, cultural impact. When the fossil, this song was released and was in the news, this man here is in the Guinness record for writing a song on a daily basis. And that day he picked the news and said, "I'm going to make a song for the cricket, for the fossil."
The call of the Jurassic era Kennedy did was simple and pure. In a travel far at night, scientists found a fossil in China. And it was well preserved, and its wings allowed them to know what it sounded like for the first time.
So his name is, and this was his song number 1135, Jonathan. So another artist asked me for the original poles I reconstructed the first time I did, I built the first poles before we make it sound nice. Was the first one, and he created this piece of art, and he deposited. His name is Peter Eudenbach. It's deposited in a museum. We should have a copy here in Lincoln, by the way. And then in this speech, the same week.
These range from the profound to the quirky. I really liked a recent amusing example which reconstructed the song of a cricket that lived 165 million years ago. But the work of science can also require courage.
So yeah, he's talking about the importance of basic science, the supporting, and this is what we were trying to do with the American embassy. Trying to tell we don't want to get involved in politics, but pay attention to what science says. Anyways, so we wrote the grant, and we ended in China. That was here already. I was already in Lincoln. And so this is Daniel Robert, my last, my boss when I was in Bristol. We ended in China looking for the living with the missing link This is the living fossils. And the idea was to, we got a liver human grant for this, and to study the wings of these animals from different perspectives and implement all the mechanical measurements of the wing into the fossils and recreate the animation of a fossil wing into that's another level. And we still, actually, we did a lot of work, and but now we are improving. We're still working on this, improving the technique. There were many species involved here in the fossil because the Chinese colleagues found more. And some of them are close to the ultrasound, some of them are low frequencies, so there was a lot of variation in there. So basically we decided to put them all together. Again, this is behavior, and this is, we suppose that the chirping is in here, it's just, it was diverse, but this is more or less the range of frequency we got. Is the T-Rex still roared like that? You see it? The larynx doesn't fossilize, the wings fossilize, I can tell. But what about the larynx? You see Jurassic Park, right? Just think about it. Anyway, and just to finish here, I'm just going to go very quickly about the hearing rings, so the other part. Just to tell you something here, just when we have the hearing system of mammals, we have the ear canal moving the tympanum, and then the tympanum moves the ossicles and convert all these vibrations into a fluid immersed, vibrations. And the cochlea has this structure, it's called the basilar membrane, that contains the mechanosensory cells. So this is tuned to low frequencies, middle frequencies, and high frequencies. That's what allows us to hear different sounds at the same time. So that is tonotopy mapping, and the sound will travel this way in the form of a traveling wave. The vibration, sorry. So we found these similarities in these animals, actually. They have the ears in the forelegs, and they have the auditory canal here. They cannot have the ear in the head because they would be too close for directional hearing, for the binaural hearing. But they collect sound here, and they move these two tympanic membranes, but they also collect sound externally. So they have two paths for each ear. So inside, they have like a cochlear organ. This is the cochlear organ we discovered when I was in Bristol. This is just the high frequency region and the low frequency region, and these cells are tonotopically organized. They do frequency mapping as well. But the ear is located, of course, in the leg. And one day, how we discovered this, one day I was sponsored by Human Frontiers, trying to see how sound propagates in this canal, and putting a laser Doppler recording in the tympanic membrane, as you see. It's a very simple experiment. Of course, you have the equipment, but it's just nothing. I was trying to see, because this tube was very similar to the hearing aid tubes. That was my interest. When by mistake I put the laser in the hard cuticle dividing, which is actually this same specimen in the hard cuticle, and this cuticle, of course, doesn't have to vibrate because it's hard. The tympanic membrane is elastic, but and then we detected that something was going on, and you see the traveling wave, and then we began to infer that 7 kilohertz will go to the low frequency in these caves, of course. When you play higher frequencies, like 30 kilohertz, they will stay in the high frequency region. That's tonotopy mapping, and we were able to see the traveling waves. Something that is very difficult to see in the mammalian ear, because accessing is difficult. You have to damage the structure. So we explored this using micro-CT scanning and to see how all of these structures look inside. And basically, they have the two things. This is a cross-section around there. And the two tympanic membranes move this plate that work like the human ossicles, and they insert the vibration into the fluid of the cochlea. Thus, and then we published this in Science, making this comparison, but we never explained how is that you can record through this cuticle. So, and then I began to suspect that we had this cuticle was transparent and the laser was going through. And it was Fabio Sari, one of my PhD students, who in his thesis demonstrated that the laser indeed goes through, and we're recording not invasively inside the cochlea. So this is good news because we can do a lot of research on this. And they have such, these animals have the elaborated ear because they need to detect the uncles and also the predators. And if you go back to this phylogeny, this family of the Katydids family appear more or less at the same time as bats in evolutionary history. The rest is the progress we have done based on this, and that drove me to write an ERC grant asking to which level is the insect ear, this insect ear, compared to the mammalian ear. To which level we can, how much we can learn. And of course we have done a lot of work on this and progress, the work of Emina showing, this is what we are doing now. I'm going to show, showing the modeling of the trachea, and this is in collaboration with Paul Squires here, and one of my postdocs. So we have to measure all the materials to be able to model this mathematically. And this is in collaboration with chemistry with Jose, measuring the materials using Raman spectroscopy. This is one of the main outputs of my students, showing that they have, the ear has to, this part is for specific communication, but the external part using this cup is for ultrasound bat detection. And this is, so I think I'm going to stop here because this is the rest of the work. This is actually being done in the lab of collaboration with Sarah Humphries. One of my postdocs is measuring the fluid dynamics, because this ear has fluid dynamic. Has this, we need to calculate, the density of these fluids to put it in the numerical models. We are also, Charlie recently showed what is the evolutionary origin of the traveling waves in these primitive crickets that live in Canada and China. And one of my postdocs is allocated now in Cambridge, trying to visualize the neural activity through the transparency of the cuticle. There is a lot of promising research because it's not invasive. So we're trying to do this. So this is my big thanks. First of all, go to the university, of course, for supporting me, the College of Science, the school, supporting me, giving me the time and the space for my research. And my current group, this is the senior postdoc and the postgraduate students, and the past members of the lab who always, of course, this is, as a scientist, you depend on the activity of your students and the group. And my main collaborators in the university, and the collaborators outside. So thank you very much. I'm really sorry to have extended for 10 minutes.
Thank you, Fernando. Given the time, I think we have time for one question, but I'm sure that Fernando would be delighted to talk to anybody afterwards in the reception. So, do we have any questions from the audience? Dan.
Thanks, Fernando, for a really interesting talk. I was wondering the similarities between the mammalian ear and the ears of the insects. What does that tell us about evolutionary processes, or how does that relate to different evolutionary processes?
So how that translates to
the evolutionary history of species? Does it tell us that structure is really forgive me if I don't know anything?
Sorry, let me make sure that I understood your question. So the similarities
between the mammalian ear,
yes,
and then the insect ears that you people pick out. What does that tell us about evolutionary processes?
Oh, the evolutionary processes. Oh, of course. here is obviously the 2 years evolve independently, but I believe if you just, I'm not sure if one of these slides I show here, that one, you see there, I believe that there were mammals here, and the cochlea of these mammals was no coil, was beginning to bend as the cochlea of the bush crickets now in there. It was a very primitive cochlea with limited, and probably they were trying to hear the animals singing. They were all singing here in the low frequencies, the mammals. At some point, the insects have to survive because to escape from the hidden range of the predator, and they have to produce higher frequency, and the ear has to couple with that. Okay? And then the mammals evolve a better cochlea. It might be more complicated. You evolve a high range cochlea for the insect, or maybe other stuff happening, and the insect evolve higher frequency. That is why when we reconstructed the call of this Jurassic, that was before bats, and they were already close to the ultrasound. So, and then I think when bats arrive, because you can see the crickets, they live here at the same time as bats, but they don't have such an elaborated ear. They might be predated, some of them, by bats, but the ear doesn't have like proper cochlea as I'm showing there. However, some crickets here that appear, there's some crickets that I didn't show here. There are arboreal crickets that one of my colleagues in France studied. There are arboreal crickets, and they sing very similar to katydids, higher frequency. There are not many species, and I bet those animals will have a hearing system very similar to the katydids. I think it's a co-evolution process there. Okay.
Thank you. So before we fully say thank you to Fernando once again, please do remember to sign up to our list in the foyer if you'd like to hear more about the new events. You can also access all of our previous events, most of our previous inaugurals on our website, which is lias.lincoln.ac.uk. And our next inaugural lecture is on the 26th of April by Professor Anna Wilkinson, who will be talking about her work on cold-blooded cognition. So if you would all join me to thank Fernando once again.